Oops, I'm sorry. I was I was doing all the introduction without microphone. So let's start again. I'm so sorry. So hello everyone and welcome to another talk in our webinar series. Today we have Denny Lee from Databricks and Denny is talking to us about reliability to your data lake using Apache Spark and Delta Lake. So before we start, a quick reminder, this webinar is also being streamed live on YouTube. You can find the link on our website or access it on our YouTube channel, LIneA MCTI. Danny, thank you very much for being with us today, and the floor is yours.
Thank you very much for inviting me. I really appreciate the time. If you have any questions, for starters, please, by all means, go ahead and chime in. I love questions, so let's start the show. So, well, as you can tell, this is about bringing reliability to your data lake with Apache Spark 3.0 and Delta Lake. I'll start with a little bit about myself. Just to provide some context, I'm a developer advocate at Databricks. Prior to my time, I actually been working with Apache Spark since 0.7, so I've been working with Spark for quite some time. Before that, I was actually at Microsoft. I was a principal program manager there for SQL Server, so I helped build some of the largest enterprise SQL Server systems, including some astronomical systems, by the way, as well. And then in the process, also was on the Project Isotope. It was an incubation team that actually brought Hadoop into Microsoft. And so I'd like to at least claim that I have some experience when it comes to working with big data systems. Now, since this audience is very much an astronomical audience, I'll try my best to tweak or talk about it in terms of that. But nevertheless, in the end, we're talking about a massive amount of data, and at least I'm hoping that I can present some of those contexts to you, folks who are listening. In case you're interested, there actually is a free ebook to learn more about Apache Spark. It's the O'Reilly book, Learning Spark, 2nd edition. You can get that for free. There's a link here, which I'll send to you afterwards. Comment in the YouTube channel, but it's right here, just dbricks.co/get-ebook. It talks about, of course, Apache Spark, but of course talks about Delta Lake, MLflow, and Qualys. And it's written by some of my coworkers, Jules, Brooke, and TD, and I happen to be one of the co-authors as well. The foreword was also by Matej Zaharia, the CTO of Databricks, but even more importantly, he's also the person who helped create the Spark project in the first place. So, and we actually have a very good VLDB paper. You can go to delta.io to read about it if you're interested in trying to understand about the concept of applying ACID compliance or ACID transactions to your data lake in order to protect the data. We're going to cover that a little bit during today's session, but in case you want to dive deeper, here is the white paper that goes with it. And the final little call out, yes, we have yet another ebook that you can potentially get for free. Not potentially, you can get for free. Go to dbricks.co/DLDG. This is the O'Reilly, early release of the O'Reilly's Delta Lake, the Definitive Guide. I actually happen to be the co-author of this book as well with both TD and Vinny. So it's right now early release, so it's a little bit raw and a little unedited, but the context nevertheless is about how Delta Lakes, how Delta Lake works. It's the guide on how to build your modern data lakehouse architectures using Delta Lake. All right. Final tidbit, what is Databricks? Well, the Databricks is the company that actually is a unified data analytics platform, or also known as the Lakehouse, for accelerating innovation across data science, data engineering, and business analytics. We're a global company with 5,000 customers and 450 partners, and we're the original creators of these popular projects, including Spark, Delta Lake, MLflow, and Qualys. All right, perfect. Now that is out of the way, let's dive into it. Now, I do actually have some additional little call outs, which in terms of if you're interested, if you want to dive deeper into Spark, there is this session with Xiaoli and Wenchen Fan about the deep dive into the new features of Apache Spark. After the session is done, and there happens to be an AMA also with Delta Lake and Spark between Barak, TD, and myself. So if you want to dive deeper into it. Okay, but let's talk about Apache Spark. Now, specifically 3.0. Now, for many of you folks, you've heard, for example, the LIneA session that myself and Colin did early on about using Apache Spark into Rock in order to be able to analyze all the astronomical data there. But what is Spark underneath the covers? Well, Spark is a really awesome big data distributed project, right? Data distributed framework that allows you to process massive amounts of data. And when it's a massively large community in which we're solving lots and lots of problems, right? And so, for example, not even the full Apache Spark 3.0 release, but the release candidate 2, right? There's a lot of things that we had solved 3,400 JIRAs, 3,400 different issues or bugs. And you'll notice that the vast majority of them were focused around Spark SQL, right? And then we also did help improvements to Spark Core and things to do with Python as well, outside the testing documents. And the reason I'm calling that out is because as big data has progressed and matured, what has become very apparent to everybody is that we need more of the Spark to be not specifically just with the Scala data engineers, but it needs to be applicable and available and easy for anybody to use within using the SQL language or with Python. And so we've resolved a lot of JIRAs specifically to make it that much easier, because that is where a lot of our focus is on, which is basically on SQL and Python. And even with the core, 16% of it being on the core, the reality is that the vast majority of it is to support actually Python and SQL, right? And as part of the Apache Spark 3.0 release, there's a lot of features that we've added in. So for some of you who have worked with large data systems, a lot of this, what you're hearing is basically solving things related to distribution of data or making things a little bit easier to work with. And in some cases, you're actually even hearing things that are related to database systems. And the reality is, yes, the answer is yes. And so that this session can't cover all of these things. And that's why I left the links to the previous sessions, because if you want to dive deeper into those, they'll actually dive into that. In fact, I'm only going to be able to talk from a high level about things like performance and extensibility and the ecosystem, and how basically how that plus Delta Lake together, these set of components around performance and extensibility, plus Delta Lake actually provide reliability to your data lake. Because in the end, that's one of the key concerns that, especially for you as astronomical researchers, you have a lot of data. You want to make sure that data is reliable. You want to make sure that it doesn't get corrupt. You want to make sure that there's protection on that data. Well, how do you do that? And so whether you're doing this as an on-premise environment or if you're doing it whether using your cloud object stores, you need to ensure that the data isn't corrupt. Any processing of that data doesn't overrun or corrupt your data lake. And then in addition to that, at the same time, you need to be super fast, right? You need to be performant. You need it to be able to run the queries quickly enough to be able to scan the data that's sitting in your on-prem environment or sitting in the cloud, right? And it can work across multiple clouds. And so this is why I will often talk about, Apache Spark and Delta Lake, because that's exactly it. It can work across all of these different environments, and they do, in fact, right? Now, switching gears, let's talk about performance. You need to be able to have high performance for interactive, batch queries, streaming, and machine learning workflows. So whatever it is you're doing to your data, you're going to need to basically make it run fast in almost any scenario. Well, one of the key things that was introduced as part of Apache Spark 3.0 was the adaptive query execution. You'll hear me refer to it as AQE, okay, adaptive query execution. I'll talk about in a second what that is. But the reason we want to call this out is because what it boils down to is that the Spark Catalyst Optimizer is also, it's basically known as the engine of Spark, right? So traditionally, when you think about databases, there's the database engine. And what does a database engine have? It has a logical optimizer, builds up some plans, builds a physical optimizer, builds up the physical plans, and then executes against those plans. That's what a database engine traditionally has. Well, in Spark, we actually have something very close to it, if not in some cases better than a traditional database engine. which is the Spark Catalyst Optimizer. Now, in Spark 1.0 or 1.x line, it was very much a rules-based optimization. For the 2x line, we had both the rule and cost-based optimization. Okay, and then in the Spark 3.0, we actually have rule plus cost plus runtime, and so pretty powerful stuff, to put it lightly. And if you look at this, basically this diagram here, forget about the red part that says adaptive planning. This actually diagram is, in essence, is the Spark Catalyst Optimizer. This idea that you have a parser that can basically parse SQL statements or your data set or data frame APIs. That's how you interact with Apache Spark. So you can do all three, SQL, data set, data frame API. Doesn't matter. The parser is able to understand all three. It'll initially create an unresolved logical plan, right? Then the analyzer will kick in and basically create the logical plan. Then you create an optimized version of it. Then you create in the planning stage, you create the physical plans, do the cost-based optimization model. So you select the physical plan, and then you run your query. Okay. Now, for those of you with a database background, like I said before, this sounds like very much what a database engine typically does, and that's exactly what it is, right? It's very synonymous to that concept, right? Now, where AQE kicks in, this idea of adaptive query execution, it's because when you're running the query, we can actually send information right back in the Catalyst Optimizer. That's what this red line is, right? Where we're basically saying, based on the statistics or the executions, what's unfinished so far, we can learn new things. And based on what we're learning, we can send that information back to the logical plan and reassess and come up with new logical plans and subsequently new physical plans and select maybe a better physical plan to go ahead and complete the query faster, okay? And this is pretty powerful because the idea is, as opposed to just simply run and done, where once you run it, you've decided how this works and you're finished. What's actually happening is you're running it, and as the system's learning, it'll optimize accordingly. And that's this idea of an adaptive query execution. And some of the key fundamentals when it boils down to AQE are things like dynamically switching join strategies, coalescing shuffle partition, and optimizing skew joins. Now, I'm going to go through these relatively quickly, but I'm going to keep it at a relatively high level in terms of what these concepts are, okay? And so when we're talking about dynamically switching join strategies, here's what it boils down to, right? When you are in orange is the representation of multiple nodes, okay? And the gray box is a representation of a table that basically spans across multiple nodes, all right? And then the green box represents the idea of a smaller table that you're going to join against, right? And so what happens traditionally before you do this concept of broadcast hash joins is that when I need to take that big table that's distributed across multiple nodes and I need to do a join against that, there invariably is a shuffle. What I mean by shuffle is that the smaller green table needs to be shuffled or distributed. The data needs to be spread across all four nodes. And so there's a lot of network chattiness. So there's a lot of communication back and forth. And so because of that, you're saturating the network between the different nodes just to go ahead and talk to, in this case, node 2, to get the table information from there, right? That will slow things down. And if it's a one-time ask, maybe that's not such a bad thing. But the reality is it's not one time, right? As you're processing data on your very large table that's distributed across multiple nodes, the reality is you're going to need to go ahead and like re-query or reassess or talk again to that green table in order to be able to achieve that join. And join, like for those who are more used to like SQL parlance, that's exactly it. Like, a join statement where you're taking like you're joining by a primary key or primary key foreign key relationship, where the idea is that you actually have two tables that you're joining together. Okay. Now, what's interesting about this is that, okay, with Spark 3.0, Spark in general, we already have the capability of doing broadcast hash joins. The idea is that it's literally broadcasting. So in other words, it takes that table, if it's that table is small, okay, that green one, it'll automatically distribute it before it runs the join statement. So that way, when that big table is trying to do a join against that smaller green table, it's actually only doing it locally as opposed to shuffling across multiple nodes. And so as part of 3.0, we also have the auto broadcast join threshold, which basically use it. You can basically go ahead and automatically do these things, or use a broadcast join hint. But the problem is that it's really hard to tune this thing, right? You might even hit out of memory errors, and if you run it into the ohm errors, basically you'll get actually worse performance because you did it. Okay, so and the reason why you can't always do the broadcast joins are things of this nature. There's a lot of valid reasons for doing that, which is like missing incomplete statistics if you've got compressed files, column stores, complex or filtering UDFs, or complex query fragments. And I'm just leaving at that just to call out the fact that there's a lot of good reasons why you can't just automatically broadcast it. Even if you can accurately determine what the size of the join table is and what the implications are, it doesn't really matter. You're going to have to, there are other reasons why we can't do it. And so what that ultimately entails is that you actually need to basically switch between different join strategies. So within Spark itself, so you don't actually necessarily need to know this stuff. I mean, if you dive deeper into it, you will. But what we start off automatically as a sort merge join. Okay, I'll actually talk about the different join strategies in a second, but that's the fundamental one we use. The reason why is because it's the most robust. It has the least likely of it running into out of memory errors, so we're going to choose that. All right, when AQE kicks in, let's just say it's trying to join two different tables. Okay, the left table is stage 1, the right table stage 2. Okay, and so when it's trying to join those two tables, it's going to initially estimate the size as 100 megabytes and 30 megabytes. Now we have a threshold of, let's just say, 10 megabytes. That threshold 10 megabytes basically means that if the second table is larger than 10 megabytes, we're not going to do a broadcast join because it's going to take up too much memory. The numbers are just randomly chosen, by the way. You can definitely set them to higher numbers, but I'm just saying that's the example I'm using here. Okay, when you execute it, though, and this is where AQE kicks in, this adaptive query execution kicks in. It recognizes from the initial pass, initial queries, from the statistics, the actual size isn't 100 megabytes. It's actually 86. And for that join table, the smaller table, it's not actually 30, it's actually 8. So that 8 megabytes means, wait, if it's 8 megabytes, we can broadcast it. And so that's actually what AQE does. So instead of in mid-flight, instead of actually going ahead and saying, we're going to stick with a sort merge join because we want to prevent memory errors, out of memory errors, we realize, wait, it's actually 8 megabytes. It's below that 10 megabyte threshold. So let's switch it in mid-process to a broadcast hash join, because then that way I can get you that query coming back significantly faster. Okay, and so this is actually all underneath the covers for Spark. So that's the call out I'm trying to say, is that there are these cool things that we're adding into Apache Spark that allow you to go ahead and get faster performance, in which you didn't really do anything. All you wrote from a Spark SQL perspective was select column A, column B, column C, column D from table 1, join table 2. You're joining on those particular columns. It's a typical SQL query. What's happening underneath is Spark is actually figuring it out. It's figuring out, okay, well, I need to use a sort merge join because that's the most robust. It'll prevent out of memory errors. But then in process, because of that AQE that's been added in Apache Spark 3.0, we're able to go ahead and optimize and change the type of join strategy it's using in mid-flight, just because we know we can get the query back faster for you. So pretty cool stuff, And then in addition to things with AQE, another really cool aspect is dynamically coalescing shuffle partitions. And so when you look at distributed data, like when you're thinking about like your standard map reduce, what it boils down to is like, for example, if you have a mapper here, right, two maps, right, and each when you're trying to basically reduce it, you're trying to, in this, organize the data by the color bar. So I'm sort of breaking it down into like color bars for the purpose of this discussion, okay? Well, what means is that there's a lot of shuffling back and forth, right? In other words, part of map one, the orange part, goes to reduce one. Part of map one, the blue bar, goes to reduce two, and so forth and so forth. There's also the shuffling that happens on map two, which says, okay, well, I need to send this to reduce one, the orange part to reduce one, blue part to reduce two, and so forth and so forth. So what's happening here is that there's a lot of chattiness, right? Going back and forth to basically go from the two mappers that you have into the 5 reducers that you have. And the other problem is that if you think about that, now you've got 5 reducers. Well, reduce 5 is the longest one, right? So it's going to take longer for it to complete. Well, reduce 1 takes about the same time, but that means I've got 3 other reducers, reduce 3, 4, and 4. Those threads are kicking in, and they're running super quick, and then they're running idle. In other words, they finish their job of reducing the data that it sees, and then it's just running idle. So even though you've executed 5 threads, really 3 of the threads are just doing nothing for the majority of the time, while 2 of the threads are doing all the work. Those 3 other threads could technically be doing something else, but they can't because they were allocated within your MapReduce environment. And so that's like, even if you don't care about the potential performance of that one particular query, because you've got yourself a concurrent environment where basically you're wanting to run multiple queries at the same time, right? These three threads are basically idle, doing nothing, which sort of sucks, right? You rather have them do something else. And so what's cool about this is that, well, then, okay, with AQE, it'll actually coalesce the partition. So it'll recognize that basically the blue, the beige, and the light blue, they actually can be coalesced together. So why don't we just put them together in the reduce 2? And so there's a lot less chattiness now, right? There's 3 sets of 2 sets of 3 as opposed to 2 sets of 5. And then now I'm only using 3 threads for your reducers as opposed to 5. So those other 2 threads can be used for something else altogether, right? So the whole purpose is to, now we're no longer saturating the Spark task scheduler. We're no longer saturating the network. We're going to be able to go ahead and dynamically, based on just looking at the data, shuffle and coalesce these partitions together. And again, from your perspective, often as the user, you're like, well, I don't care. I don't need to know this stuff. And that's true. And that's actually more or less the point. Like, underneath the covers of any distributed system, and for that matter, even when you're looking at database, right? You're writing the select statement, but there needs to be things like this where it comes to like the impact of disk speed, the impact of the network. How do you improve those things so that way the users don't actually have to know that's going on underneath? Well, again, Apache Spark 3.0 with AQE, it's advancing that concept massively, where it basically making the performance of your queries run significantly faster. Same query, same select statement that you ran, but underneath the covers, we're making it that much faster for you. Okay. And then finally, dynamically optimizing skew joints, right? This is another big thing. And what I mean by that is, often there's a concept of when you're, for example, joining 2 different tables together, there's a skew. Like, for example, if you're looking at data warehousing style queries, for example, there's a null value. So, and the vast majority of the values are null. So that means you're skewing. This happens in databases all the time, where basically all the values of the primary keys are null or -1. So then all of a sudden, one thread is just spinning to process all the -1s because you're going by that primary key or by that clustered index, okay? This happens for almost any database style system, data lake query, all the above. Ultimately, what happens here, just to provide some context here, is that, well, you're going to have a skew. Well, that means when I join table A part 1 with table B part 1, table A part 2 with table B part 2, the color coordination that we have here, they'll all run relatively quickly. But table A part 0, table B part 0 are going to take a very long time, okay? Because that thread is just going to keep running, and until it processes all the data, in table A part 0, it won't finish. So your query doesn't finish. Now I'm going to skip the next couple slides because it's just providing the underneath the covers of what's going on. But what I really want to do is basically call out this. With AQE in Spark 3.0, what happens is that instead of it just going with the threads, the thread count that you see here, it'll automatically break down that table A into its own set of sub-partitioning or splits. So instead of one thread trying to access all of table A part 0, it'll get, using this example, we'll split it into 3 automatically. Okay, and by splitting the 3 automatically, now the thread has only approximately a third of the data for it to process. So yes, more threads are kicked in, but the point is they're all approximately the same size now. And so table B is replicated, similar to this concept of the broadcast hash join that I talked about before. So that way now it's a local shuffle that's happening between the part 0 split 0, part 0 split 1, and part 0 split 2. Ultimately, again, that's happening underneath the covers for you. So by doing that, now your query runs significantly faster. So instead of having one thread that's stuck on trying to do all of the processing for part 0, we split it into 3 automatically under the covers, and then bam, you get faster query performance. This is a quick example with this, okay? If we're running on, this is using a Databricks runtime, but this happens also for Apache Spark. If you're actually able to go do this, basically with AQE off, the numbers you see, lowers better, okay? So these are just example queries that we run from, I believe, TPC-DS benchmark queries. So the blue basically is with AQE off, and the reddish orange is AQE on, right? And as you can tell, the queries are significantly faster once we go ahead and turn on AQE. Same query, is just that we turned adaptive query execution on now. So pretty cool, okay? Let's see, what else? Okay, lots of other stuff that's kicking in. So there's also, for example, again, underneath the covers, this idea of dynamic partition pruning, okay? The key principle here is that it's trying to avoid scanning the entire partition by using the query results of other query fragments. This is particularly important when you're doing OLAP style star schema type queries. It actually improves the performance of your TPC-DS benchmark as well, right? Middle enough astronomers probably don't have as much TPC-DS type queries, but nevertheless, the idea is that you can improve the query performance. And again, same idea. With dynamic partition pruning off, which is in green, in red, orange, it's with dynamic partition pruning on, lower is better. Basically, you have a speed up of anywhere between 2 to 18x faster. And again, you don't actually need to know this. I'm actually going to skip the next couple of slides because that's actually providing details of how it works underneath the covers. But you actually don't need to do it as astronomers. When you're running your queries, this is actually happening for you. So I think I'm sort of probably getting the point across quite nicely that basically the Apache Spark ecosystem is still rapidly growing, and it allows you to go ahead and basically make it easy for you to basically improve the queries of your performance of your queries, excuse me, especially when it comes to massively large amounts of data sets. Okay. And this example, I'm going to hand you guys the slides, by the way, so you'll definitely have access to them. So you'll have links to everything that I have here. But the key call out basically is like, if you want to dive into it, I actually have slides that explain the concepts of how DPP actually works underneath the covers. But I just jumped to the last slide, which is of this particular thing, which says 90+% less file scans. So if you're scanning that much less, fewer files, you can have actually massively faster query performance. And this particular example that I chose, it was like 33x. Pretty cool, right? So again, pretty rock solid stuff. All right. I've been going at a pretty fast pace just because I have a lot of other stuff to cover too. So I did want to cover this thing. If you care about running the join hints yourself, in other words, if you wanted to dive deeper into it, here is a pretty a succinct sort of like a high level the summary of what you can do. Remember, sort merge join is the most robust environment way to do joins, and you don't actually even need to technically include the statement in your select query, because by default it does do a merge. But if you need to do a hint and you need to tell it, I know the data really well, so I need it to do a sort merge join, no problem, just add the merge statement. Same thing with a broadcast hash join. If you know that even though if the statistics are wrong, and in fact that second table is small, you can tell it to do a broadcast versus shuffle hash versus shuffle replicate. The point is that, usually Spark will be able to figure it out on its own, but not all systems are perfect. So we provided the hints as well. So you can go ahead, and if you happen to know how it works with the data, you can provide hints to tell the join how it should go ahead and handle the data. Okay. Any questions before I switch over to extensibility and ecosystem? Okay, I'm going to presume quiet means we're good to go. So let me just dive into that. So there's a lot of cool stuff that actually has happening with the ecosystem, like data source v2 API, Java 11 support, Hadoop 3 support, Hive 3x Metastore, and Hive 2.3 execution. Basically, there's a lot of really cool stuff, but I'm going to try to do this relatively quickly because I need to talk about how all of this together gives you your data lake reliability. Okay. And so specifically the data source v2, let me talk about what is the data source API, like for folks who are basically trying to understand a little bit underneath the cover of what's going on, right? The data source API is about, allows you to have compatibility of the Spark data frame API. And it could not leverage the dataset API. Now, what happened is that in Spark 1, we actually had a data frame API, which allowed you to run, in essence, Spark SQL queries against your data set. So it introduced us this idea of Spark. But as part of Spark 2.0, what we did was introduce this idea of a dataset API, and the data frame API actually leveraged the dataset API. It allowed us to have things like type safety and much faster performance. So that we absolutely wanted to have the data frame API make use of the dataset API. Now, for you who are running SQL queries, you probably don't really care, honestly. But the point is that underneath the covers, when you're running a Spark SQL statement, we're using this dataset API that gives you both type safety and faster query performance. Well, the original data source API couldn't actually go do that, right? It actually was still using the old data frame API. This meant things like information about the physical storage, like partitioning and sorting, from your source system, whether it came from the underlying cloud object store, from underlying on-premise system, or for that matter, even a database, okay? That information about physical partitioning, sorting, that information Spark could not understand what it was. It never knew about that information. So the Spark optimizer couldn't make use of the fact that, like, oh, I know that you've partitioned your data this way, or you sorted your data this way. So just some of the performance improvements that you just saw with AQE, it can't do any of it because it's going like, well, I don't know this information. You haven't passed it to me, right? And the extensibility was not good. So because we couldn't push down some of those queries directly to the underlying storage systems or database systems to actually improve the performance. For example, if I knew that as I'm running a query against a database that I could potentially use an index to improve performance, well, I can't. If data source v1 did not allow me to basically make use of things like that. So there's basically a bunch of issues here, right? But the one super important thing when it comes to data reliability was this one, okay? Which is the right interface was so generic or so general, it does not support transactions. So one of the things that's super important, especially, like I said, I came from the database world, is that, databases certainly, I still love databases, but they certainly have their problem when it comes to working with very large amounts of data. The fact is that you could always try to shard a database, but the maintenance of it, even if I was to use a cloud, like cloud AWS RDS, or, Azure SQL Server, Azure SQL, excuse me, or whatever else you wanted to use, right? The reality is the maintenance of this thing is gigantic, and not to mention also expensive. And so that's why we resorted to storing a lot of our data into a data lake, which is great. But how do you ensure that you actually have ACID transactional compliance, i.e. supported transactions, i.e. when you write something to the disk or to storage, that either it completely writes completely or does not write it, right? You don't want it, for sake of argument, to write 95% of that file and then fail, right? If it writes 95% of the file and fails, you don't know if that file is actually valid for querying or not anymore. So you want it either to be 100% or 0, right? You want to be clearly, it's written down. That's basically what the whole purpose of transactions. Now, in the case of database systems, the transactions were often tied to this row system. When it comes to data lakes, we actually often had to do the transactions, down to the file level. But whether you're talking about file level or row level, the point is that either it wrote it or it didn't. Well, when it comes to data lakes, you don't have that. And the data source v2 API allows a generic interface so that way it does support transactions. So that way, whatever mechanism you store your data, a Spark can actually support the idea of a transactions. So in other words, Spark, when it writes to disk, it'll actually support this idea, assuming the underlying storage system supports it. It'll actually support the idea of like, okay, either you wrote it or you didn't. It was a 100% right or it completely failed, okay? I know I'm sort of harping at that, but when you're dealing with very, very large systems, the reality is that's what it comes down to, okay? Now, there's also other interesting things like catalog plugin API. This allows us to, for example, write in Spark statements like create table and alter table. That's cool. That's interesting, but that's also incomplete. That you want to write other DML statements like updates, merge, and update, merge, and delete. Excuse me, right? And so, as of Delta Lake 0.7, and by the way, I forgot to update the slide. Let's note the fact that we recently announced Delta Lake 1.0 as part of the Data and AI Summit that recently happened. But once you go from Delta Lake 0.7.0, from that version onwards, we actually support Spark 3.0 and add support for metadata defined tables and SQL DDLs. Okay, so what do you mean? What does that mean? Right. Well, the idea is that, okay, now with Delta Lake and Spark, in addition to when I write the create table and the alter table statement, which it then gets stored in the Hive metastore, so that way you can use table names like events as opposed to the file path as the name of your table. I know intrinsically for people who work with databases, you're going, wait, you use the file path for a table name? Yes, that's actually a common scenario when it comes to these type of environments. Well, instead, you actually would just rather use the table name. That seems to make much more sense considering it's called a table anyways. But what happens now is that because of Delta Lake and Spark together, you're able to not just do the create table and alter table. You have your insert, you have your delete, you have your update, you have your merge. You have all of these additional DML statements, data manipulation language statements, data definition language statements, right? So that you have all that capability. So underneath the covers, basically now you have all of the ability to run full SQL, not maybe not full, but more complete SQL statements that you're used to running within your database's typical environment. Now you can absolutely do this with Spark and Delta Lake put together. And the key thing about bringing reliability is not only do you have the capability to do these updates or merge statements, but you have transactional protection underneath the covers for all that. And that's what Delta Lake does. So what's happening under covers when I, for example, running a DML statement like a delete or an update or whatever. So I want to focus on delete right now. So when I want to delete some data from my files, for sake of argument, I want to delete, 2 rows, okay? That's what is represented by this yellow here, okay? So when Spark's running with Delta Lake under the covers, okay, the process is basically, if I would normally have to go ahead in order to delete, and this is for any distributed system. Spark's not the only one that has to do this. What happens is that we actually go ahead and copy all the rows from the table, i.e. the gray ones, from the files that we're not deleting, and we're creating a new set of tables, okay? Sorry, a new file, okay? So that's pretty brutal, right? That you have to do all of this, okay? Now, in reality, that's exactly what's happening. But in the case of Delta Lake, you don't have to physically write the statements to do all that, which is select star from table, okay, that where everything is not yellow. Insert that into a new file, table / files, delete the old one, and then go ahead and rename the new one. You don't have to, that's what you normally would have to do. In the case of working with Spark SQL Delta Lake, you literally just go delete from events, and that's it. And yes, there is a version 2 of that table that's created, but underneath the covers, all that really happened was that I just grabbed the data. Again, you didn't have to do any of this. I selected all the data that wasn't yellow, propped it into a version 2 gray. The transaction log itself points to this new file. So when you say look at the table, the event table, it'll automatically point to version 2. Because we have these different versions, you can actually have this concept of time travel or data versing that's within Delta Lake, matching SQL, Spark SQL with Delta Lake. So in other words, if there was some mistakes that happened, for example, version 3, you put the yellow data back in, which is what this example is. Version 4, you deleted it, and then you need to go ahead and put some orange data in. Whatever happened, you can actually still go back in time and realize, wait, you know what? We made a mistake in version 4. Let's just go back to version 2. Well, in this case, because we do all of this underneath the covers, you can just literally go select star from events, but then you add the moniker version as of. That's it, version as of, and then whatever version it is. And so now you can go back in time, go to a previous version of your data lake, grab that data that you needed, and go ahead and restore it or build a new version of the table based off of it or whatever else. Right. So if somebody deleted the data by accident, guess what? You didn't actually delete it. It's a placeholder for the deletion, but it actually didn't delete itself. So what actually happened instead was that we created a new version of it, and you can then go back in time and grab that version. Now, there are things about how long of a retention you have. And then I'm actually going to cover that right now, which is the files themselves as a delete file retention duration. Basically, by default, we're going to retain 7 days of data. Now, we actually won't delete it ourselves. You have to then run a vacuum statement. Now, you can automate that if you want to, but the vacuum statement basically says anything that's older than 7 days will automatically remove. So that way, if you've got like lots of versions of your table because you're constantly doing inserts, updates, and deletes to that table, that's okay. Then you'll regularly run a vacuum, and anything that's older than 7 days, you can go ahead and automatically remove that version, those older versions. And you can modify that interval. So instead of 7 days, maybe it'll be 5 days, or maybe 30 days, or whatever it is that you decide. Log file retention, which is basically how long you keep the history of that table. So often for GDPR purposes, right, you're gonna need to know, even if you don't have the data, you want the historical context of saying, okay, yes, we had vacuumed the data at this time, we had deleted data 30 days ago. We didn't actually have to keep the version of it, but you needed to have something that states very clearly that I deleted the data 30 days ago. Okay, well, that's what the transaction log contains for you. So that can get also very large as well. So you can absolutely control how long you retain that for. And then for any environments where you actually need to retain all of history, what you can do is and this is very common, you basically generate a new table based off of your transaction log, and you store that as a separate table purely for the purposes of GDPR compliance, risk compliance, things of that nature, right? So that way you can actually still have fast performance, because the more files you add to the system over time, it'll require more threads or more costs. And so that we want to give you those things to control. But ultimately, what it boils down to is that with this data source v2 and your catalog API integration, what happens is now you're able to go ahead and work with Delta Lake like this, where now you can actually have your DML statements. Now you can have time travel. Now you can have transactional protection around your data. So that way, whenever you modify that data, whenever you change it, whether you're using Scala or Python or SQL, doesn't really matter. you can ensure that any time there's data being written to your storage, that there's transactional protection around them and done in a very easy way. And whether you have multiple users trying to access or write to the table at the exact same time, that's what Delta Lake allows you. It protects the data, so that way, if you get two people trying to write, like update or delete a table at the exact same time, just like in any database, there's actually those transactional protections around them. And so, everything when we were just focusing on Spark 3.0 was very much like we got faster performance, faster performance, faster performance. The key crux, though, is that yes, that absolutely enhances your reliability of your data lake because you actually can make use of it and you can get the queries back faster. But in the process of having so many people be able to query that data and run processes and all these other things, what invariably happens is you'll have high concurrency, or at least concurrency, where multiple people are trying to read and, more importantly, write to that data lake at the same time. Well, how do you protect it? How do you ensure that the data doesn't get corrupt by accident? Having this integration with the data source v2 and catalog API from Apache Spark 3.0 with Delta Lake allows you to have that capability now. And then I did want to sort of finalize with these two concepts, right? Improving SQL DMLs and DDLs and DMLs asset transactions are just a start. Okay, like what we're trying to explain is that, and this is very much your concept when it comes to as you're doing research, right? What you want is and this is what we often term as a Lakehouse Paradigm, right? You want the improved performance with data warehouse-like capabilities, but you want all of that on low-cost cloud object stores, or, for example, your on-prem Hadoop environments. But the reality is that as you are all sharing data, often you're going to be using a cloud environment. It doesn't matter which one, right? It doesn't matter if you're using Google Cloud Storage, Azure Data Lake Gen 2, S3, right? You want to make it easy to share that data. You want to make it easy to go ahead and run high-performant data warehousing queries, but on that low-cost object storage. And so that's what the Lakehouse Paradigm is. And at least part of this is addressed extremely strongly because of the things like Apache Spark 3.0 and Delta Lake, because now you have that reliability similar to like what you see for the data warehouse, because you have asset transactions to protect the data, but you're doing all of it on exactly these low-cost object stores. So that's really it. If you want to know more about Delta Lake, by the way, you go ahead and you can build your own using delta.io. So please join us there. If you have actually any questions, the Slack and Google group are right there, so you can go ahead and chime in. I'm going to leave it at this with 10 minutes left. So if you have any questions, you can definitely ask me. But again, I'm going to hand these slides out to y'all. But if you want to learn more, there's a whole bunch of different references right here, whether it's our tech talks, whether you want to try Databricks itself, the ebooks that I mentioned, the VLDB paper, all of it's here. So by all means, please go ahead and try out Spark 3.0 and Delta Lake right now. If you all, because this is an astronomical environment, I encourage you, if you all want to get together and talk to me more about all this environment, join the Delta Lake Slack channel. Okay, it's on delta.io. I'll even create an astronomy channel for us, right? And then we can start having those conversations. So I definitely encourage you to come join us, because we are all working on solving some pretty large problems. And obviously you guys take the cake when it comes to really, really large problems. Okay, I think that's it for me. Any other questions, or I want to hand it back to you guys now.
Thank you, Danny, for the very interesting question. For the very interesting seminar. We now have some time for questions from the audience. If you joined us on YouTube, you can put your question in the comments section, and I will redirect them to Danny. And if you joined us on Zoom, you can raise your hand and ask it yourself. So questions? While we wait for questions, I have a question regarding the time travel technique. How does the disk space usage is handled in all different versions? when you have?
That's a great question. So when you're thinking about time travel, like I oversimplified it by only talking about a few files, like, or one set of files. The reality is when you're doing a deletion or an update or whatever, you're not typically modifying all of the files. Like, for sake of argument, you have 100 files that make up a table. Okay, let's just say when you're doing let's just use deletion because that's the easiest to explain, right? Typically, you're only impacting maybe 2 or 3 of those files when you're doing the deletion. So what happens is that we're going to, in essence, replace those 3 files. Now, the 3 files still exist. It's just we generated 3 new files without the yellow, whatever we delete, right? And so then the table is made up of the other 90-some files that didn't change at all, plus the 3 new files that you have. So underneath the covers, what's happening is that you have a transaction log. That transaction log basically lists out all the files that you have. So version 1 contained the original 100 files. Version 2 contained the 97 original files plus 3 new files. Okay. And by the way, it's important to call out the reason why the transaction log is so important. The reason why it's so important is because what's happening is that, especially when it comes to cloud object stores specifically, the problem that you run into is that the listing of the actual files from a cloud object store is really, really slow. So for example, if I'm running on my Mac and I go, ls-lsga, and to list out the files in my root folder, that actually comes back relatively quickly. If you try to do that in a cloud object store, that actually is not fast. It's actually slow. And it's even slower when I have lots of data. Instead of just dealing with hundreds of files, I'm dealing with thousands of files. So if I have to list out the files, that becomes really, really, like that startup of listing files becomes excessively slow to do. So the transaction log, what's really cool about it is that it actually contains the list of all the files that you need. So you never have to list out the files. So when Spark is asking Delta Lake, hey, give me the files, it's not saying go to the file system and list out all the files for me. What it's saying is that, no, you have the transaction log, here's the 100 files you need. And it automatically gives it to Spark. So Spark, they never have to do that initial list of the cloud object store. So again, significantly faster. And all I did was just simply give you the list of files as opposed to simply going ahead and making you run a list, right? But so we've took the advantage of what's coming known as MVCC, multi-variable concurrency control, right? Which basically allows us to have multi-version concurrency control. Excuse me, not multi-variable. My goodness, I'm tired. But the context is basically that by having these multiple versions of the files, you have the advantage of writing the files extremely quickly, so that way you reduce the I/O. You can do the deletion at a much later date. That's what the vacuum is. And at the same time, you have the time travel, because what's great about time travel is then, oops, I didn't mean to delete it. Well, it's okay. You can go back to the original files. You're good to go.
Okay, well, thank you.
Sure, that's fine.
Rodrigo, can I talk?
Yes, sure. Go ahead.
I apologize, but I'm having problems here with my machine. Danny, fantastic talk. Thank you very much, especially for all the references that you're putting here available to us. I do have a question. I mean, we can go in more detail later, but what bothers me is that it's like, for instance, what we have normally is a process where you have a data set. You have 2 different processes. You compute something, and then you want to join. I can see how Spark will benefit for us in this second stage. But what about the first stage? And how can we integrate these 2 types of processes in a single environment? This has always bothered me a bit.
Sorry, what was the first stage again? The second stage was the join. What was the first stage?
You have the 2 processes which are basically bag of tasks that you just run things to compute certain values. At the end, the result should be combined. So I see Spark as a substitute for the database, basically, but not necessarily to manage the process, parallelization, etc.
Oh, okay. So actually, Spark absolutely handles the parallelization. That's exactly what it does. So if you're, by any chance, Luis, are you familiar with Hadoop?
I'm sorry.
Oh, are you familiar with Hadoop?
Yeah.
Okay, perfect. So the whole concept of Hadoop was basically this idea of massive parallelization. That's why we have this concept called MapReduce, right? And so Hadoop brought this whole world of massive parallelization based off of querying the file system, right? Like, we tried to build databases that were massively parallel data warehouses in the past, right? And in the end, the key problem when it came to us building massively parallel data warehouses is that the storage engine and the compute engine were tied or coupled so tightly to each other and within a database, where basically there was a reliance on knowing exactly what the storage was and what the compute was and how to align them together perfectly. And it gave you no flexibility, right? That's why databases were proprietary systems, because there was no flexibility. It was their proprietary file system with their proprietary compute engine, and that's it. Now, they may have been based off of the similar algorithms, but nevertheless, it was their proprietary implementations of it. Now, in the case of Hadoop, why I bring this up is because the whole premise is saying, well, there's nothing proprietary about like a Parquet file, or nothing proprietary about a bunch of CSV or JSON files. So Hadoop was basically saying, well, let me just go run MapReduce on any file system whatsoever, so that way I can have massive parallelization. What it was really good at was parallelization, but it couldn't put stuff into memory to give you back faster performance. So when I was, for example, working with Yahoo, we would often be working against these really large, like 2 petabyte clusters, and this is back in 2010 or 2011. So that, at that time, that was massively large, right? And that's great. So yes, the query might have taken a week to finish, but at least it finished, right? As opposed to, because we could parallelize that. And so what Spark does is basically take that same concept of parallelization, except it's actually able to make use of memory much, much, much more efficiently. And so because it's able to do that, now you have both that massive amount of parallelization, but actually done on with much faster performance. So when I talk about all of these other things, like, within Spark itself, like, yes, I was talking about AQE because I was talking about database concepts and all these other things, but the baseline for Apache Spark right from the beginning absolutely was the fact that it was designed right from the get-go for massive parallelization, massive number of tasks to be spread across multiple systems. That's exactly what it's designed to do. So, okay. Yeah. Hopefully that answers your question.
Well, we can follow it up later on. Okay, thanks.
But sure. No problem at all.
Thank you, Luis. More questions?
Hello, do you hear me?
Yes, sure. Go ahead, Eduardo.
Okay, thank you. Denny, thank you for the nice presentation. I have 2 questions for you. First of all, can you elaborate a little bit on this concept of adaptively building the result of a query? What are the kind of techniques that you are using here? Are there some kind of heuristic or some machine learning technique or what?
Okay, so I think you said 2 questions, but I only really heard one, which is
the second one, the one has to do with this MLlib, which is a Spark library. What is the level of integration of MLlib with Delta Lake?
Oh, got it. Perfect. Okay, so first question's about AQE. Honestly, I kept everything here at a very high level. I'm not trying to not answer your question. It's just that it's good. It's a really long answer, okay, on what's going on with AQE. But the long story short is that we don't have a lot of machine learning, at least not yet per se within AQE. It's more about being able to understand the statistics as scans of the data are happening. We're actually compiling a bunch of statistics, and then we can use those statistics to better reanalyze, recreate the logical plan, the physical plan for your data. Now, in the future, could we potentially be using machine learning to help us do that? Absolutely. Not going to debate you at all on that one. But what I'm saying is, at least right now, underneath the covers, that's basic. What we're really doing is we're just able to make use of the statistics in mid-flight, as opposed to waiting to the end. inside this presentation, which I'll give to you, there are absolutely links specifically to AQE. There's actually much better people who presented this stuff. So I'm going to have them go ahead and explain it. Okay. And specifically, it's Marianne Su and Allison Wang. They actually have a great session specifically on the deep dive details of AQE. They're the experts on that one. And so I'll let, they will do a much better job explaining it than I will, being very candid. But underneath the covers, that's basically what's happening. Okay. So that's the first part. In terms of the second part, in terms of MLlib, MLlib is for anybody who doesn't know, is basically Spark's machine learning library. We're not very fancy with our names. Okay, great. It's just literally MLlib. Okay. Now, the machine learning library has a lot of really cool things in it within Spark. Now, is there anything tied to specifically Delta Lake? There is not, but not because you can't use MLlib within with Delta Lake. Quite the opposite. In fact, for example, I have a blog post called Productionizing Machine Learning, which in fact talks about how Delta Lake helps you productionize your machine learning environments because of the different versionings, because of the ACID transactions, because of you have streaming data coming in, and you can protect that data with ACID transactions, and you can run your machine learning algorithms trustworthy. The reason I'm saying there's nothing specific is because since MLlib's part of Spark, and Spark using, for example, as we called out in today's session about the catalog v2 API, the data source v2 API, things of that nature, you're automatically getting the integrations with Delta Lake. So because it's MLlib's part of Spark, you're automatically getting that. And so while there's nothing specific for MLlib, because it's part of Spark, yeah, your MLlib, and for that matter, any other Spark component is able to make use of Delta Lake right from the get-go.
Okay, great. Thank you again.
Sure. No, glad to answer your questions.
Thank you, Eduardo. I think we can have a last question. Another question. Well, if not, I will take the privilege of asking a second question. Danny, you might know, you might be aware that Python, it's a very popular language among astronomers, and for the last years, Jupyter notebooks also. Is PySpark is a library written in Python to use to do queries in Spark, or am I mistaken?
Oh, no, it is. I mean, more specifically, what PySpark is, and yes, absolutely, Python, super popular language. No debate on that at all. Quite, and so long story short, PySpark is a Python abstraction layer on top of Spark. Okay, that's the short thing. What does that mean? It means you can run Python statements to run Spark in Python. Okay, well, PySpark, but it's Python based. Okay, you're using the Spark methods. So if I'm being completely candid with you, it's not as Pythonic as some people would look because of the way the methods have been created. But nevertheless, it is absolutely Python for you use Spark. And underneath the covers, because Spark Engine is actually written in Scala, but you don't have to know any Scala, right? With PySpark, basically that's all abstracted away. Now you run in Python. Now, there's a whole bunch of things I want to talk about, which I can't talk about. In fact, if you want, we can even have a separate session specifically on this. But the excessively long story short is that within the Python is a very, very important component to the Spark community. We have things like vectorized or pandas UDFs, and also things like koalas, or as part of Project Zen. Project Zen was a project that we introduced about 1.5 years ago, specifically to say, can we make basically Spark more Pythonic? All right, more Python friendly. For example, typical Scala errors. Like again, like I have to do another session for you to because I can go on forever on this one. But basically, typical Scala errors, you're going like, really? I don't want to read a stack trace that's 5 miles long, right? Like, I mean, Python can actually still provide some pretty horrible stack traces, but at least from a Python perspective, it makes more sense. The Scala ones make no sense whatsoever if you're used to Python, right? So that's what we're doing. Project Zen, that's one small example. It's like, can we at least provide errors that actually make more sense to the Python people? But more importantly than that, for example, Koalas is the Pandas API. Okay, so in other words, if you're used to using Python with pandas to run your machine learning or to do any of your data manipulation queries, we get it. If you're starting off on your local machine, especially if that's what you're gonna do. Like, I get it. I did that myself that's how I started off too. But how about if I want to say, well, I want to run Spark, but I don't really want to learn how to use Spark yet, right? I mean, eventually you will, honestly, but you want to just write pandas, but I want to be able to run that on really large data sets. So that's why we built Koalas. The Spark community together, we built that. So that allowed you to go ahead and say, no, just use the same pandas APIs that you're used to using. And then underneath the covers, we're actually going ahead and running Spark queries, but go ahead and continue using it. Once you get super serious, I can definitely see you saying, well, now I really want to manipulate. Okay, manipulate in PySpark. You still don't need to use Scala. Maybe you want to do more than what the Pandas API does, but you can still write this in PySpark. You don't have to write this in Scala, because whatever you do with Python in PySpark, you're going to get the same performance, except for UDFs. And that's been solved. Well, not completely solved, but mostly solved. And that's the concept of Pandas UDF. So for example, in your case, especially because when the astronomers are using, like, let's just say they're using these Python libraries, right? How do you distribute it? Well, to oversimplify this concept, because the actual implementation is always going to be the devil in the details. But in essence, you're building you'll build a Pandas UDF around the Python library or the Python function that's using that Python library that you're using. Okay, and because you're using it as a Pandas UDF, you'll be able to use Spark to automatically distribute everything. So in other words, it's no longer stuck running on the driver on a single node. It's running on all the workers, all the task workers, basically. So now that query is distributed. And so, like, there's still going to be some gotchas, like anytime where you're doing shuffles or a distinct or whatever else, where basically it does need to merge or coalesce into a single driver at some point. But as a general statement, if you can run it as a Pandas UDF, i.e. for vectorization, then with Pandas UDFs, you can actually go ahead and automatically do that. And so those are just two of the things I can immediately think of for the Python community. And there's a lot more than that. Like I said, that's actually worthy of its own separate conversation, as a presentation. And glad to do it, by the way. Just saying, like, don't happen to have the slides handy right now. But the context very much is, yeah, like, if you are in the realm of Python and you don't want to use SQL and you don't want to use Scala, absolutely. Like, it is, we've spent an exorbitant amount of time specifically ensuring that for the folks who are in the Python world that don't ever want to leave the Python world, they can be very comfortable with using PySpark, to the point where actually we're currently working on, and in some cases we've already done it, but it's an ongoing process where even the error messages that you're getting back are much more Pythonic, let alone anything else. Okay, so I definitely encourage anybody of you who are in the Python world, absolutely, to go ahead and check out PySpark. Yeah.
Well, that's awesome. Thank you, Denny.
Of course.
Okay. If there are no more questions, I think we can. We will now wrap this up. Just this presentation will be available on our website and on LIneA's YouTube channel. And also for the next week's webinar, we will have David Depern from the INAF, Rome Astronomical Observatory, and he will talk about near-Earth asteroids, risks and opportunities. So thank you everyone for attending, and a special thanks for Denny for taking the time. Thank you, Denny. And I hope to see you all next week. So everyone, have a great week. Bye-bye.
Thanks, Danny. Bye.
Thanks very much. Appreciate it. Bye.
Bye-bye, guys.
See you. Bye-bye, people.